guys, I'm Biji. If you've looked at the NEET papers of the past few years like I have, you probably noticed that some terms associated with enzymes like apoenzyme, holoenzyme, coenzyme, these come up a lot. But what do they mean? It's all here in this video. So when you think of an enzyme, what do you usually think of? Let me guess. It is this spherical monster sort of gobbling up pizza slices? Well, we all tend to do that. But you know that's not the true shape of an enzyme. Enzymes are proteins. Not all of them, because we do have RNA enzymes, but most of them are. Which means that they are basically a chain of amino acids. And how these amino acids connect with each other will determine how the protein folds. And this in turn determines the structure of the enzyme. And just like any protein, the structure is pretty complex. What you see here are the three common representations of what a protein or an enzyme looks like in the 3D form. This is a common digestive enzyme, carboxy peptidase. And what you have here is its ribbon model, the spacefill model, and the third one is the wireframe model. Don't worry, you do not need to draw these. What you probably need to draw is your spherical monster. This is just to give you an idea of what an enzyme truly looks like. Now, anything that breaks the integrity of the structure will destroy the function of the enzyme. If the protein is broken down or denatured, then the enzyme will not function, which is why the structure of the enzyme is very important for its function. Now, although enzymes are proteins, most enzymes are not protein alone. They have a non-protein part which is very essential. And it is the protein and the non-protein part put together that forms the fully functional catalytic enzyme. This is called the holoenzyme. And the protein alone part of it is called the apoenzyme. And the non-protein part which binds the apoenzyme is called a cofactor. Now, did you get that? Yeah, it's pretty simple, right? But to remember this, let's put it in the form of a formula. Holoenzyme equals apoenzyme plus cofactor. Here's a mnemonic. The HOL or the whole part of the holoenzyme is like WHOLE, whole. So the whole enzyme or the holoenzyme is the complete active enzyme, and it contains both the protein and the cofactor. The protein alone part or the apoenzyme can be formed from one or more protein subunits, and they come together to form this structure, which can also be called an apoprotein, which is a more general term. The apoprotein or the apoenzyme need cofactors to complete them. Now, the cofactor can either be an organic molecule or a metal ion. And if it is an organic molecule, then it's called a coenzyme. Coenzymes are usually derivatives of vitamins. So they're just functional groups that come by and give the enzyme certain properties that it did not possess. But regardless of whether it's a coenzyme or a metal ion, these cofactors are very essential for the enzyme activity. Usually they're part of the active site, the site where the substrate binds the enzyme and the catalytic activity takes place. So they probably play a role in stabilizing the enzyme substrate complex. But even if they are not part of the active site, they may play a role in modulating the enzyme activity. That is, it can either turn on or turn off the enzyme or increase or decrease the enzyme activity. And the cofactors are really playing it cool, you know. They sort of drop by, assist in a few chemical reactions, and then bye-bye and scoot. Well, most of them, not all. Some of them are really frantic. And they're tightly bound to the apoenzyme through very strong bonds, including covalent bonds. And these are called prosthetic groups. Alright, now you know what everything means. But you probably want examples. Well, even if you don't, your exams will probably ask for it. So let's dive in. So let's look at the enzyme carboxy peptidase again. As I already mentioned, it's a digestive enzyme. And if you look at the name, it indicates that it's a peptidase, meaning that it breaks down peptides or proteins. And it's a carboxy peptidase, indicating that it breaks down proteins at the C terminal or the carboxy terminal of the protein. whereas an aminopeptidase would break down proteins at the N terminal or the amino terminal of the protein. Anyway, coming back to the point, carboxy peptidases have zinc as a cofactor, and this metal ion is bound tightly to the enzyme. If you remove this metal, then the enzyme does not work. So this is part of the active site, and it plays a crucial role in stabilizing the substrate in the transition state. And the coenzyme NED is a cofactor in many different enzymes. If you study the chapter respiration in plants, then you probably know of these enzymes. They are all on the Krebs cycle. Pyruvate dehydrogenase, isocitrate dehydrogenase, malate dehydrogenase, well, basically all the dehydrogenases. They have NED as a cofactor. NED, or nicotinamide adenine dinucleotide, is basically a derivative of vitamin B3, which is nothing but niacin or nicotinic acid. Similarly, FAD, or flavin adenine dinucleotide, is also a cofactor in one of the enzymes of the Krebs cycle. The enzyme is succinate dehydrogenase. And FAD is a derivative of vitamin B2, which is nothing but riboflavin. Now these two are basically cofactors, that is, they bind to the enzyme transiently, help in the catalysis, and then dissociate. Whereas the metal ion of the carboxy peptidase is a prosthetic group, that is, it stays bound to the enzyme all the time, even when catalysis is not taking place.